Hello everyone, welcome to tutorial number 7. So let us start with question number 1. So we define first what we call as full binary tree, and it is a binary tree where every internal node, and by internal node I mean the nodes which are non-leaf nodes. So every internal node has either 0 child or 2 child, and h of n is defined to be the number of full binary trees which has n plus 1 leaves. Okay. So we have to derive a recurrence relation for this h of n. So let me first demonstrate the value of h of n for some small values of n. So if I consider h of 1, that means I want to find out the number of full binary trees which has 2 leaves. And there is only one full binary tree which has 2 leaves, namely this binary tree. By the way, here I am not interested in the label of the nodes. I am interested in only the structure of the nodes. Okay, so there is only one possible structure of a full binary tree possible which has 2 leaves. What will be h of 2? So there are two structurally different full binary trees which has 3 leaves. This is binary tree number 1. This is binary tree number 2. If I consider h3, h of 3 basically denotes the number of structurally different full binary trees with 4 leaves. So this is one of the trees, this is second tree, this is the third tree, and this is the fourth tree. Okay. As I said earlier, I am not focusing on the label of the node. So you can't say that a tree where this node root has label A1 and the leaves have label A2, A3 is different from a tree where the label of the root is A2 and the leaves are A1 and A3. No, I am not focusing on the label of the nodes. I am just focusing on the structure of the tree. That's all. So my claim here is that the number of full binary trees with n plus 1 leaves is same as the value of nth Catalan number. And for that, what we can do is the following. Either you can try to derive a recurrence relation explicitly for h of n, but we won't do that. Instead, what we will do is we will say that we will establish a bijection between the set of full binary trees with n plus 1 leaves nodes and a set of all ways of parenthesizing n plus 1 values to specify their multiplication order. And we know already that the number of ways of parenthesizing or the cardinality of the number of ways of parenthesizing n plus 1 values is nothing but the nth Catalan number. We already know that. So if we establish a bijection between the set of solutions for this new problem and the existing problem whose solution we know is Catalan number, then we are done. And the bijection is easy to formulate. I'm not giving the exact details, but just giving you a high level idea. So I have to do the following. I have to take each and every full binary tree with n plus 1 leaves, and corresponding to that I have to specify what exactly is the parenthesizing or multiplication order that I can formulate for n plus 1 leaves. So the n plus 1 leaves, I call them as x0 to xn. So in this case, my n is equal to 1. So that's why I am taking the case of 2 leaves. My 2 leaves are x0 and x1. And the only possible parenthesizing here is that I want to multiply them because I have a kind of a balanced tree here. Whereas if I consider this tree for the case where n is equal to 2, right? So this is one possible multiplication ordering and this is another possible multiplication ordering. The multiplication ordering corresponding to these two trees are respectively this. So you can interpret here that this tree is left intended, that I am going down first left. So that's why x0 is multiplied with x1 first, and then whatever is the result that is multiplied with x2. So treat it as follows: x0, x1, x2. Whereas the next tree that you have x0, x1, and x2. So it is equivalent to saying that x0 is going to be multiplied with the product of x1 and x2. If I take the case of n equal to 3, that means 4 leaves, then this ordering corresponds to x0 dot x1 dot x2 and then multiplied with x3. Okay, right, so that will be the order. X0 getting multiplied with x1, then that result getting multiplied with x2, and that result getting multiplied with x3. Whereas if I consider this tree, this will be equivalent to x0 multiplied with x1, that is getting multiplied with x2 and x3 here. So it is x2 and x3 that gets multiplied, then their product is getting multiplied with x1, and their product is getting multiplied with x0. Okay, so that's a bijection here. Okay, in question 2, you are given the following. You are given a square grid where you have the coordinate 0, 0, and you want to go to the coordinate n, n, and you have cells here, and the only movements which are allowed to you is that you can, at a time, you can either go one cell either to the right from the current cell or to the top of the current cell, and you have to find out the number of valid paths. Okay, so for instance, one valid path could be that I go top from the current cell, and then again I go top, and then again I go top, I go top, and then I do right, 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 and right. Whereas I can take a path where I go right and top, right and top, 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 right and right. Right? Whereas I can't do the following. I am not allowed to do the following, that I go right and right and then again come back left and then top and then bottom, and no, I can't do all those things. That's not allowed. The only movements that are allowed are one cell at a time, either to the right or to the top. So for solving this or finding the number of valid paths, I do the following. So imagine this is the set of all your valid paths, and you have another set consisting of another set which denote the set of all strings of length 2n, and the 2n length string has equal number of R symbols and T symbols. Okay, that's the second set, and my goal here is that I will show that there is a bijection between these two sets. And if indeed there is a bijection between these two sets, then shows that the number of valid paths is nothing but the number of strings of length 2n, which has equal number of R symbols and equal number of T symbols. And we know that the cardinality of this latter set, namely the cardinality of the set of all strings of length 2n, which has n number of R symbols and n number of T symbols, is 2n choose n, because it's equivalent to saying that you have 2n positions, and out of those 2n positions, you have to find out the n positions where the R symbol is going to be there. Because once you identify the n positions where the R symbol is going to be there, the remaining n positions have to be occupied with the T symbols. Okay, and the bijection is very simple here, right? You take any valid path, right? It will have definitely n number of R movements and n number of T movements, because you are at position number 0, 0, and you have to go to the position number n, n. The number of R movements and the number of, first of all, the number only movements are the right movements and the T movements. So I can imagine that each time I make a right movement, I put down a string, I put down a character R. And each time I make a top movement, I write down the character T. So definitely I have to make n number of r movements and n number of t movements. It can't be the case that the number of r movements is more than the number of t movements or vice versa, because then definitely that's an invalid path. Okay, and the bijection is very straightforward here, right? The third question is, how many diagonals are there in a convex polygon with n sides? So again, we can derive the formula using induction or some other mechanism, but we will count it directly. So imagine you are given a convex polygon consisting of n sides and where the vertices are v1 to vn. Now let's focus on some arbitrary vertex v of I and try to count the number of diagonals that we can have where v of I is one of the endpoints. If vi is one of the endpoints of the diagonal, then the other endpoint of the diagonal can't be the immediate neighbors of vi, namely the vertex number vi plus 1. That can't be the endpoint because the edge, because vi comma vi plus 1 is not a diagonal, it's a edge of the convex polygon. In the same way, the other endpoint of the diagonal can't be the vi minus 1 because vi and vi minus 1 constitutes an edge or a side for the convex polygon, and the side of a convex polygon can't be treated as a diagonal. So that means with vi as one of the endpoints of the diagonal, uh, I can have n minus 3 diagonals. Why n minus 3? Because excluding these three vertices, namely vi, vi minus 1, and v of I plus 1, all the remaining n minus 3 endpoints can be the other endpoint of the diagonal, with vi being vi being one of the endpoints, right? So now it turns out that the total number of diagonals will be n times n minus 3 over 2. Why over 2? Because what we did here is, with v of I being one of the endpoints, I have n minus 3 diagonals. So that means with v1 as one of the endpoints, I can have n minus 3 diagonals. With v2 as one of the endpoints, I can have n minus 3 diagonals. And in the same way, with v of n as one of the endpoints, I can have n minus 3 diagonals. So if I sum all of them, that gives me the total number of diagonals, but I will be counting the diagonals twice. Uh, I will be counting some of the diagonals twice, namely the diagonal with the endpoints vi comma vj will be counted twice, because with vi being one of the endpoints and the other endpoint could be anything, I would have accumulated n minus 3 diagonals. One of the diagonals there will be the diagonal where vj is one of the endpoints, and the same diagonal will be counted when I will be focusing on the case where vj is one of the endpoints and the other endpoint could be anything including vi. Okay, so that's why, to compensate or to remove that overcounting, we are dividing it by 2. Okay, and this will be the case where n is greater than or equal to 4, because if the number of sides is 3 or less than 3, then we can't have any diagonal. So for instance, in a triangle, you don't have any diagonal. Okay. In question number 4, we are interested to find out the number of triangulations of a convex polygon. So let T of n denotes the number of triangulations of a convex polygon with n plus 2 sides. And what's basically a triangulation? It is the process of dividing a convex polygon by non-intersecting diagonals. So if my n is equal to 3, right, that means I have 5 sides. So I'm taking the case of a pentagon, and there are 5 ways of triangulating it, okay, by non-intersecting diagonals. Okay, so now I want to find out a recurrence relation, or want to find out the number of ways of triangulating a convex polygon with n plus 2 sides. So I will find that by formulating a recurrence equation and by showing that the solution for that recurrence equation is same as the nth Catalan number. So imagine you are given a convex polygon consisting of n plus 2 sides, which has the vertices v1 to v of n plus 2. Now, to solve my problem of triangulating a convex polygon with n plus 2 sides into smaller problems, I consider an arbitrary edge. So for simplicity, I take that arbitrary edge to be the edge or the side uh, Vn plus 1 and Vn plus 2, namely the side with endpoints Vn plus 1 and Vn plus 2. Okay, and it turns out that this side Vn plus 1, Vn plus 2 can be the part of only one triangle in the overall triangulation, right? Okay, that means if I fix the third point Vk, where the Vk could be any vertex in the set V1 to Vn, that will fix the triangle in the triangulation, which could result in a triangle where one of the sides of the triangle is Vn plus 1 comma Vn plus 2. That means I'm focusing on the case where uh, so for instance, if I could have a case where, okay, I could have taken the case where this Vn plus 2, Vn plus 1 being one of the sides of the triangle, and the third point would have been V2. But even in that case, this edge Vn plus 1, Vn plus 2 can be part of only one triangle. It can't be part of multiple triangles because of this reason that we are interested in doing the triangulation using non-intersecting diagonals. Okay, so I will be dividing my problem into smaller problems depending upon the third point or the third vertex of the triangle involving the edge Vn plus 1, Vn plus 2. So the third vertex Vk could be any vertex. It could be the vertex number V of 1, in which case uh, my triangle would have been something like this. Okay, or my vertex Vk could be vertex number V2, in which case my triangle would have been something like this, and so on. Right? So now, once I fix the third vertex, namely the vertex Vk, the overall polygon with n plus 2 sides will be now divided into two smaller polygons. The first polygon P, right, which has the vertices, this portion, this vertex number V1, the V2, V3, Vk, and the side Vk comma Vn plus 2, and the last side being Vn plus 2 comma V1. So it will have k plus 1 sides. And how many ways I can triangulate the polygon P? Since it has k plus 1 sides, as per my definition, n plus 2 side convex polygon is triangulated in Tn number ways. So k plus 1 side polygon will be triangulated into T of k minus 1 number of ways, or T of k minus 1 number of triangulations are possible for the polygon P. And the other polygon being the polygon Q, which will have n plus 2 minus k sides. Namely, the starting vertex will be Vk and the side Vk comma Vk plus 1. Then the next side will be Vk plus 1 comma Vk plus 2. Then all the way to the vertex Vn plus 1. And the last side being the side Vn plus 1 comma Vk. Okay. And as per my definition of T of n, the number of ways of triangulating Q is T of n minus k. So these many triangulations for P and these many triangulations for Q, along with the triangle where the three vertices are Vn plus 1, Vn plus 2 and Vk, gives me all possible triangulations where one of the sides is of one of the triangles is Vn plus 1, Vn plus 2, and the third vertex of that triangle is Vk. Okay, so from the product rule, it comes out that the total number of triangulations, with this being one of the triangles in the triangulations, is T of k minus 1 into T of n minus k. Okay, but now my k can range from 1 to n. Okay, my k could be vertex number v1, my k could be vertex number v2, and so on. So if I take the summation over k to, so take the summation over k being equal to 1 to n, then I get the total number of triangulations for a n plus 2 sided convex polygon, and this is the same as the recurrence relation for your nth Catalan number. And your initial conditions will be this: t of 0 is 1. T of 0 means the number of triangulations for a two-sided convex polygon. Well, a two-sided convex polygon can't be divided or triangulated, so no way of triangulating. I am denoting as one way. T of 1 means the number of ways of triangulating a convex polygon of three sides, namely the triangle, and the triangle itself is the triangulation of itself, so that's why there is only one way. T of 2, that means the number of ways of triangulating a rectangle. Okay, so this is one possible triangulation, and another possible triangulation for the rectangle will be if you draw this. So there are two ways of triangulating a rectangle. That's why T of t will be 2, and from 3 onwards the recurrence will trigger. The last question is, we want to find out a recurrence relation for the number of derangements of n objects. So just to recap, a derangement of n objects is a permutation of those n objects such that none of the objects is at its correct position. That means the object number 1 is not at its the first position, object number 2 will not be at the second position, and so on. So we can divide the set of derangements of n objects into two categories. Okay, so and for these two categories we consider or focus on the element which is there at the first position. So we are considering the case where at the first position we have the element ak, where ak could be either a2, a3, or an, and with ak being occurring at the first position of the derangement, we can have two categories of derangements. Okay, category 1, where the element a1 is occurring at the kth position. And remember, element a1 is allowed to be occurring at kth position in a valid derangement, because at the kth position we are not putting ak. Ak has already occupied the first slot, and in the kth slot I can have either a2, or I can have a3, or I can have a4. So I am considering the case where at the kth position the element a1 is there. So if that is the case, that means I have already deranged two objects. The kth element is deranged and it is now shifted to the first position, and the element a1 is also deranged. It is no longer occurring at the first position but rather occurring at the kth position. If that is the case, then my problem boils down to the problem of deranging the remaining n minus 2 elements. So I am still left with the problem of deranging a2, a3, a of k minus 1, a of k plus 1, and a of n. So I am still left with n minus 2 elements, and whatever way I could derange them, you take any derangements of this n minus 2 elements. In that derangement, you add the following positioning. You put AK at the first position and you put A1 at the kth position. That will give you a derangement for the n elements. And as per my definition of derangement, there are d of n minus 2 ways of deranging the n minus 2 elements. So this gives you the first category of derangements where ak is occurring at the first position. The second category of derangements with ak occurring at the first position is the following. You don't have the element a1 allowed at the kth position. That means element a1 can take any other position. Of course, it can't take the position a1 because at the first position you have already put the element ak, and you are not allowing the element a1 to occur at the kth position as well in this second category of derangements, right? So these are the only two categories. Having fixed the first position or having reserved the first position for element ak, you have only two choices or two categories of derangements possible. One category where at the kth position you are allowing a1, and another category of derangements where you are not allowing a1 at the kth position. So we are considering now the later category. So if a1 is not allowed to occupy the kth position, then I am still left with the problem of deranging n minus 1 elements. Okay. Why n minus 1 elements? Because even the element 1 is now supposed to be kind of deranged in the sense that it is not allowed to be occupying, it is not allowed to occupying the kth position. So that's like a restriction with respect to element a1 itself now, right? So as per my definition of derangements, there are d of n minus 1 ways of deranging n minus 1 elements. So you find out those derangements, namely the derangements of n minus 1 elements, and in that derangement, the element a1 won't be occupying the kth position. You take any such derangement and add the element ak at the first position, that will now give you a derangement of n objects where element ak is occurring at the first position and element a1 is not occurring at the kth position, and this will be your later category of derangements. And if you sum these two derangements, the number of derangements in category 1 and the number of derangements in category 2, that will give you all possible derangements where the element ak is occurring at the first position. Okay. Now, since there are n minus 1 options for a of k, so my a of k could be a2, my a of k could be a3, my a of k could be a of n. And for each possible a of k, I have d of n minus 1 plus d of n minus 2 number of derangements. Okay, so that's why the overall formula for the number of derangements will be n minus 1 times the summation of d of n minus 1 plus d of n minus 2. With that, I end tutorial number 7. Thank you.